In this video, let's cover an example of homogeneous differential equation. We have 4xy dx plus x minus y times x plus y dy equal to 0. So step 1 is we want to check, is it homogeneous? Is it of the following form, m dx plus n dy equals 0? Well, indeed it is, because we recognize that our m is 4xy, and we recognize that our n is x minus y times x plus y. And step 2 is, are m and n of the same degree alpha? Does this equality hold for m? And does this equality hold for n? Where the idea is that if we replace x and y times a multiple t, then that t should come out raised to some degree alpha outside of the function. And same for the n. So let's see that. Plugging in for m, we have the following, and then plugging in for n, we have the following. In either cases, we can see that a t squared comes out. We have t squared here, and we have t squared here, and these are the original functions for xy, x minus y times x plus y. So yes, m and n are homogeneous of the same degree alpha, where alpha equals 2. And further, this implies that our equation is homogeneous. Now step 2 is we want to substitute either u equals y over x or v equals x over y, whichever can make the equation simpler. In our case, I have a hunch that plugging in for v might make it simpler, so let's go ahead and try that. Let's do v equals x over y. So x will equal v times y. Plugging that in, we should get the following. And now, step 3 is if we had u, we substitute for dy, and if we had v, we substitute for dx. Of course, we have v, so we substitute for dx. In other words, using the product rule, dx becomes v dy plus y dv. Plugging that in, we get the following. And now that we have expanded this out, our next goal is to simplify into a separable form. So first things first is we're going to distribute this term into these two terms, and we can see that we have a common y here and in here. So we're going to factor the y out of here and a y out of here. So doing that, we have this. As you can see, we successfully distributed, and we got the two y's out. That became a y squared. Canceling the y squared, and then obviously the y cubed, it goes 1 degree down, it goes 2 degrees down to a y. We get the following. And now I'm going to FOIL this, or distribute them together, and we get this. V minus v cancel, and putting all the terms in front of dv together and all the terms in front of dy together, we get this. If we divide the 5v squared minus 1 and the y over, we get the following. And now we are successfully in a separable form, where the terms of y are here and the terms of v are here, and they can be separated. So now step 5 is to solve the separable variable. So we subtract the terms of v over, and we have this. We go ahead and integrate. And next, we want to do a u sub, where we let u equals 5v squared minus 1, and then du will equal 10v dv. And then v dv will equal du over 10. Plugging in for 5v squared minus 1, and then plugging in for v dv, we shall get the following. Also, we went ahead and integrated dy over y. It became natural log of y. And then 4 over 10 will simplify to 2 over 5, and we integrate, and we get natural log of u. I'm going to go ahead and multiply the 5 over. Next, using the log power property, these coefficients or constants will go inside and be raised to a power. Same with the 2. So we get the following. If you take e to the power of on each side, the natural logs undo themselves, so we get this. We have the c because e to the c is a constant c. Now if we multiply the y to the 5 over, we get this. And recognize that the product of two absolute values is also an absolute value. Now we can go ahead and plug in for u, and we have this. And further, we can plug in for v, and we have this. Now this looks a little messy, so I'm going to go ahead and clean this up. I want to distribute the y squared over the denominator. Taking the y squared out of the square, it becomes a y to the 4th in the denominator. The y to the 4th cancels, and the y to the 5th gets reduced down to a y. And we end up with this. And this shall be our solution. We want to further analyze this, so let's go ahead and clean the slate. Now this expression by itself would be simple to analyze, but the fact that we have it inside an absolute value makes things quite interesting. And to see that, we go ahead and split the absolute value. We take the power to outside of the absolute value on the left, and we take the square root on both sides. The plus or minus of c is just a constant c, so we can just rewrite it as such. Now we can see that we have 4 possible cases to analyze. And how do we have these 4 cases, you may ask? Well, we have 2 absolute values, right? We have this one, and we have the one inside the radical. Now this absolute value breaks up into a positive and a negative case, and this one also breaks up into a positive and negative case. So combining those 2 for each, we have 4 possible cases. So we generate our table of cases, where for the rows, we want to focus on this absolute value. So we have y greater than 0 and y less than 0. And for the columns, we want to focus on this absolute value. So we have 5x squared minus y greater than 0 and 5x squared minus y squared less than 0. So first case becomes this, where we have positive and positive. So just multiply a plus 1 and a plus 1 inside here. Second case, we have negative and we have positive. So we get this, where we multiply a negative 1 inside the radical. And following this logic, we can get the remaining 2 cases. And this is how we will build our curve, by looking at these 4 cases. Now further, if we rewrite the differential as a derivative, dy dx, we get this. Right away we can see that y squared minus x squared cannot be 0 because it is in the denominator. Splitting the y squared minus x squared into this, we can further see that y cannot be negative x and y cannot be x. So these are our singular curves, meaning these are points on the graph where if the solution crosses, it does not exist. So we go ahead and generate our slope field. First off, I'm going to include our singular curves. So we have x equals y, and we have x equals negative y. Okay? And now I'm going to include in the solution for the case 1. Okay? Right now constant is set to 0, so essentially this just becomes kind of like an absolute value function, y of absolute value of x, but multiplied by some constant. Now, if we let c go to negative 100, we can see a parabola sort of forming. But if we get c to the positive side, towards positive 100, it splits into a hyperbola, but only on the positive y side. Okay? Now let's bring this back to 0. And instead of case 1, let's bring in case 2. Where it is essentially the same thing, but because we have the negative inside the radical, everything is flipped over the x-axis, so it's on the negative side. Okay? And I'm moving this constant from the negative to positive. Now let's bring it back to 0. Now let's go from case 2 to case 3. Where now it seems like it's like case 1, but it's not exactly, because if you go to 100, you go to the positive side, you go to the parabola. But if you go to the negative side, you get the hyperbola. And it may look the same, but it's not, because if we bring back case 1 with it, we see that where case 1 is a parabola, case 2 is a hyperbola, and where case 1 is a hyperbola, case 2 is a parabola. So their order flips, okay? And that has to do with the first absolute value. And similarly, if you take case 1 and case 3 out and bring in case 2 back and then case 3, we get the similar looking pattern where it's the same thing, but their order is flipped, okay? And if we bring all 4 curves together, we get this cool looking 6-sided star pattern. Isn't that cool? Now keep in mind, of these solution curves, points on this graph where they cross it cannot exist.